OS-aware IP development methodology. In this paper, we propose the OS-aware IP development methodology. The main purpose of this methodology is to enable both hardware co-design and verification prior to building matured SoC, thus contributing to the reduction of total development period for mobile APs by securing early verified software and hardware IP. The proposed methodology adopts a co-emulation of QEMU simulation and hardware emulation. Most of IPs such as CPU, eMMC, LCD, and peripherals, which are frequently for Android platform boot up, are allocated to the QEMU simulation side, which maximizes the runtime performance of the software. The only target IPs and memory subsystems are allocated to the hardware emulator side to help start the hardware software platform are developed with the RTL, the register transistor level design. Except the target IP, all of the IPs have the QEMU library models which are already verified. It is fast to bring up the platform, including compilation and dwelling time. Proposed transactions for external communication such as memory storage, CPU and PCIe BFM bus functional model operate the same ways as real hardware devices work, and proposed memory coherent interfaces reduce emulation time by a mild count of communication. Application results show the booting for Android platform can be completed within the 10 minutes on the proposed methodology, and show the software driver IPs performs as successfully developed and validated RTL before the silicon-based development board is ready. Finally, the proposed method also helps enhance quality of software by saving more time for design and validation for software developers. 1. Introduction. Due to the increment of SoC size and complexity, there are a lot of potential technical bugs and issues which can be detected by hardware software co-verification only. Since hardware software co-verification is usually performed by the running a real application on the full SoC emulation at the last stage of the design cycle on a cycle or on a silicon box, or issues that are detected by co-verification can delay an entire project schedule. To resolve the issues by ECO, engineering change order, software workaround, or even respins. In mobile AP industries, several solutions have been proposed for the reduction of hardware software co-verification TAT. One of the representative solutions is the hybrid emulation platform, which we will describe in section 2-3, where the CPU is replaced by the ARM-fast model as software emulation to accelerate the boot-up speed of OS in full SoC. This emulation methodology in general resulted in achieving more than 15 times speedup on OS booting compared to the conventional full-chip hardware emulation, which we will describe in section 2-2. Because the ARM-fast model is not a cycle-accurate model, but functional accurate model (FA model), which is beneficial for full SoC software validation point of view. From the viewpoint of IP design and verification, however, there are some constraints to use the hybrid emulation platform directly. When we are interested in verifying our target IP or other IPs are supposed to be running properly such that other IPs do not cause any side effect such as counterfeiting kernel panic, lockup, and so on. However, it's not the case because the maturity of other IPs are not that higher either. Also, porting entire SoC to emulation is still heavy and slow, so we propose a new methodology to remove all dependency and constraint with achieving 5 times faster Android bootup than hybrid emulation platform. 2. Related research, previous work. This chapter introduced conventional SoC developed flow focusing on software development and verification environment include accelerating by emulator. At the beginning of project, simulation is the best choice to verify IPs and a component because it is easy to set up environment and the fastest compile time. Once RTL is getting mature, the emulation is used to. After basic pure SoC emulation is passed, hybrid SoC emulation setup starts to run with the OS. Simulation. At the beginning of the IP design and verification, RTL simulation is the best candidate for following reasons. It is easy to set up simulation environment including generation test bench and test vectors. Also, compilation time and loading time is much faster than emulation. Before RTL is stable, there are a lot of iteration of both RTL itself, TB, vectors, and vectors because of bug fix. However, simulation speed is inversely proportional to the design scale. As the design size grows, simulation speed reduces exponentially. In the case of several hundred of billion gate scale, simulation speed can be dropped to a few dozen kilohertz. This simulation speed is 1/6 power times slower than the silicon speed. Therefore, the SW software switch runs during the 1 second and the silicon can consume the 10 power of 6 seconds, 11.6 days for simulation. It is almost impossible for simulation to be used for software development and verification with a long time duration. 2-2 Pure emulation. Once RTL is matured, meaning that the basic functionality checks are finished, it is time to port RTL to emulate to accelerate RTL simulation. It's known the speed of emulation is 10,000 times faster than our simulation. This emulation speed can be from the several hundred kilohertz to several megahertz. The emulation speed is 10 power of 3 times slower than silicon. It can be applied to a software development and verification. Also, software which runs during 1 second and on silicon can consume the 10 power of 3 seconds, 16.7 minutes for running. The emulation can be adapted to develop the software, such as device drivers, which are relatively simple. However, it's not fast enough to be used for the development of the Linux kernel and Android platform, which are relatively large scale and complex, because it can't take more than 10 hours to boot Linux and Android using emulation platform. Because of the TAT turnaround time constraint, full chip SoC emulation is used to use only for bare metal test or Linux-based simple software initialized test. 2-3 Hybrid SoC emulation methodology. Hybrid SoC emulation methodology is the best solution to overcome the TAT or constraint of the pure hardware emulation. It uses co-emulation methodology. CPU and memory components are allowed to ESL virtual platform side with the TLM or LT loosely timed models because they issue a lot of transactions during a boot up time of the Android platform. Other IPs are allocated to a hardware side, emulator side. because CPU emulation on fast model, which is FA model run over Linux host server, so it is much faster than a real CPU over emulator, which run 5 MHz actual operating frequency. As shown figure 1, only CPU and the memory are virtualized to accelerate performance, and there are transactors to communicate between virtual platform and emulator. As the result of a hybrid SoC emulation methodology, it only takes 49 minutes and 15 times faster simulation speed for Android boot up compared to the pure hardware emulation systems. The figure 1 hybrid SoC emulation methodology. The 2-4 conventional SoC development flow. Hybrid SoC emulation development methodology is fast enough for early software bring up for Android, but as shown in figure 2, it is set for a few months before an MTO master tape out. It is because it is full SoC-based CPU hybrid. There are steps which are necessary to build the platform. All IPs inside of SoC should be verified integrated SoC, and drivers should be ready. So as IP software developer's perspective, it's not enough time to use the hybrid SoC emulation methodology to develop and verify their software over the OS Android. 3. Proposed platforms. We focused on IP design and verification view. The goal is to do the software hardware co-design and co-verification as early as possible. To do this, we have built a platform such that all components related to the OS booting are located at the virtual side, and the target IP and the related components are located at real emulation side, as shown in Figure 3. Figure 3, basic concept. We used the QEMU to emulate above the virtual side environment, as it is already verified open source. Since the OS boot up, the benchmarks, application installation, and loading them are mainly performed on virtual side. Time for the initialization of the IP can dramatically reduce, such as that is 5 times faster than hybrid platform. Moreover, all IPs you set target IP are located at the virtual side, hence we do not need an unnecessary time to validate the hardware software for those IPs. For example, we used to spend almost 1 month to reserve other IPs on a hybrid platform, such as audio IPs Counter Panic, and 2D and a 2D compositor, IP segmentation and so on. These problems can be caused by 2 factors. The first factor would be from the IP bug from the RTL or the relevant driver. Another factor could be totally different time domain between virtual emulator, leading to the counter panic to do a timeout. So this methodology could enable IP developers to concentrate on target IP itself. Software developers could also start their work if they are a functional model for IP by putting function model on virtual side. When the RTL becomes ready, we can easily replace the function model with real RTL stimulus. The following such chapters explain more detail about how to implement further usage model and how to validate. 3-1 the transactors for communication host Linux and emulator. Host Linux machine, runtime host, and emulator connected by PCIe prefer component interconnect express, so all of a transaction through PCIe, and the concept of the transactor is now common industry solution, which consists the front end interface and back end interface by physically interconnect PCIe. Figure 4 shows the example of the PCPU BFM bus functional model transactor. Front end interface control transaction for reading and writing data from post died. Backend interface for converting those transactions to bit signals and target IP and are physically connected by a bitstream bit signals. In this paper, there are only 3 transactors for CPU and GIC, general interrupt controllers, and the coherent memory interface. But if the target IP needs more transactors, such as a camera or a sensor or so on, it is easy to generate or use vendor-supported transactor library named AVPI, Accelerated Verification IP. Figure 4 transaction diagram. 3.3.2 is the memory coherence between the shared virtual memory and emulator. This chapter explained about the emulator communication issues followed by a memory coherency. The bandwidth of the PCIe is usually enough even though it is highly depending on a PCIe version and a configuration. It's up to 32 GB per sec as current emulator. So the bandwidth is not a bottleneck nowadays, but the problem is latency overhead. For example, once target IP that is in emulator sends a bit level transaction for reading some data from a CPU TLM that is post Linux, the backend interface converts the bit level transaction into PCIe transaction with the address and command and send to the front-end interface through the PCIe. Then the front-end interface reads data from a host Linux and transfer those data through PCIe to backend interface. And finally, backend interface convert to either bit level transaction and send to the target IP. During this transaction sequence, that is TPI function call, the emulator's user clock is stopped to keep the latest value, which means the clock is not proceeding until the transaction is finished. Hence, it causes significant latency issue and affects the entire emulation performance. Moreover, it is hard to reduce latency because the latency is affected by the various conditions such as fixed time and BIOS specification, operating simulator, and host Linux condition. So it is next to reduce communication count between target IP and CPU as less as possible to enhance this emulation speed. Below, the experiment shows that how it is important to reduce communication counts and how it can be optimized. According to the PCIe specification, 4 GB data read transaction only takes less than 1 second. However, it may take more than 5 seconds in the real emulation, depending on the various conditions. One way 4 byte transaction takes 5 milliseconds 5 to 7 microseconds and on PCI specification, but it may take 14 microseconds and the best on real. Let us have more extreme situation. Another extreme situation. If this transaction is supposed to read 4 GB from host Linux and it sends 4 byte read transaction for 1 GB times, it'll take us over 7 hours. But if the transaction sends 64 bytes read transaction, it will take only around transactions. It will take only around 10 minutes. To overcome latency issues, as mentioned before, memory is required to be existed not only in host side but also emulator side. If the memory exists only host side, emulator would frequently stop the clock whenever target IP accessed the memory in host side. The host memory inside the emulator side, the memory inside the emulator side can be a cache, buffer, and real memory model like LPDDR4, depending on the target IP characteristic. But the most important feature is coherence. If the coherence between host side and emulator side memory is broken, it will cause a critical function bug. If there are a lot of communication between memories of both sides for coherency, the emulation performance significantly will be dropped by the latency issues. So some of the technique and assumption are used. When a target IP needs to read data from DRAM and CPU, CPU prepare sorry when a target needs CPU prepare data to DRAM, control target by CPU BFM, and then IP target IP reads data. Yeah. And this where is the end? When the CPU needs to read data from DRAM, assuming that the data is modified by target IP raises interrupt by GIC. GIC BIM. Okay, good. So memory coherence is updated right after CPU BFM and GIC BFM operation done. If the target IP behavior is different as these assumption, it is necessary to use timer or instruction counter which upcoming CPU's instruction, and when the timer is and counter values reach the setting value, they communicate to make coherency. 3.3 Further usage of 4 IP evaluation platform. Since the selection of right IPs for each mobile AP application processor is important, it is unavoidable to perform the evaluation of PPAB, performance, power, area, and bandwidth, among candidate IPs under the same environment, and should be evaluated before SoC integrated starts. For the evaluation, there are a lot of consideration points for selection of a GPU, such as a vendor, IP version, and configuration, such as how many shaders, cores, size of L2 cache, and so on. To evaluate the GPUs with each configuration, the environment should be small for parallel emulation, but represent real memory subsystem for accurate evaluation by using proposed methodology, and it is really simple to set up the environment for evaluation by replacing target RTL and putting driver from vendor deliverable. Yeah, 3.4 validation platform. To validate our new methodology, we applied our new platform for GPU IP verification as shown in the figure 5. In this figure, the common platform stands for an Android-ready virtual platform. Target IP is the GPU software and hardware, and related bus traffic and memory and transaction is to communicate between the common platform and the target IP. The memory subsystem, including the bus component, should be the same as real SoC to evaluate performance and verify the functionality. Also, the memory transactor supports the same hashing equation. Figure 5 shows proposed methodology and validation platform. Okay, the figure 5 proposed methodology and the application result. We used GFS benchmark 3.1.0 Manhattan at 1080p with a 300 millisecond fixed step-up time. It takes 10 minutes to boot up. Android Marshmallow, 8 minutes to do the APK loading using ABDB. Android Debug Bridge, and a 45 minutes for learning for benchmark. And because it only takes 7 minutes to the APK loading time for rendering, one frame takes 1.8 minutes for average. Figure 6 shows the rendering the result of Manhattan and Angry Bird application that are performed on our proposed methodology, and Table 1 shows the summary of our experimental result. In this table, pure emulator is the case where the full SoC is loaded to the real emulator, and hybrid platform is the case where CPU inside the SoC is replaced by the virtual CPU located on the virtual side. It is noticed that our proposed methodology is 5 times faster than a hybrid platform, as described before. Because the only target released RTL is allocated emulator, it is possible to consume the small capacity of emulator and so fast compile comparing hybrid SoC emulation. Table 1 is performance comparison. Figure 6 is the resulting image. The conclusion. In this paper, new emulation methodology was presented such that this makes it possible to starting development and verification of IPs from the early stage of design cycles and speed to speed up the verification compared to the traditional hybrid platform. The new methodology has been used in our IP development flow, such as we were able to find many software bugs between firmware and driver, or RTL bugs with the real benchmark over the OS, or even before the full SoC RTL integration was finished. This helped us avoid huge design time that could have been wasted for debugging. Future work will be covered power analysis flow over Android to find out peak power and analysis to optimization. The figure 6 proposed IP development flow. Okay, thank you. References key. Okay, thank you for your time and this is the reading of the paper, the OS Aware IP Development Methodology DVCON2019 in US. Thank you again.